Section: Introduction. In this section, we introduce large language models, LLMs, that have been pre-trained on extensive internet datasets, showcasing their effectiveness in various areas like text generation and language comprehension. Their broad training allows them to adapt to different tasks, such as coding help, education, and healthcare. This success has led us to explore their potential in decision-making problems, which are central to agentic AI systems. We hypothesize that LLMs can make informed predictions about actions without needing extensive interaction with their environment, thanks to the world knowledge embedded in them. Additionally, the chain of thought (COT) method helps these models reason about their past actions, aiding their interactions with the environment. However, we find that these advantages do not always translate into strong performance in decision-making tasks. Research indicates that LLMs often struggle with exploration, leading to less effective behavior. This issue, along with the knowing-doing gap, where models understand what to do but fail to act on that knowledge, presents significant challenges for developing more capable agentic LLMs. Our goal is to understand why LLMs frequently underperform in straightforward decision-making situations. We systematically investigate three common failure modes in small to medium-scale LLMs: greediness, frequency bias, and the knowing-doing gap. Our analysis reveals that LLMs often choose actions too quickly, resulting in limited exploration of possible actions, leaving up to 55% of the action space untested. We also observe that smaller LLMs tend to favor the most common actions regardless of their effectiveness, a behavior we call frequency bias. Larger models reduce this bias but still exhibit greedy behavior that hampers exploration. We quantify the knowing-doing gap, finding that while LLMs can articulate how to solve a task correctly most of the time, they often prioritize greedy actions instead of acting on their knowledge. To address these issues, we propose reinforcement learning fine-tuning, RLFT, using self-generated COT rationales. Reinforcement learning is a key approach in decision-making and has shown success in various fields like gaming and robotics. We examine the impact of RLFT on pre-trained Gemma 2 models of different sizes in multi-arm bandit and contextual bandit settings, as well as in a textual tic-tac-toe environment. Our findings indicate that RLFT improves LLM's decision-making by enhancing exploration and reducing the knowing-doing gap. Despite these improvements, the exploration strategies of LLM agents remain suboptimal. Therefore, we evaluate both traditional exploration methods used in RL and LLM-specific strategies to enhance fine-tuning for decision-making tasks. In summary, we contribute by analyzing three failure modes in small to medium-scale LLMs in decision-making: greediness, frequency bias, and the knowing-doing gap. We explore how RLFT on self-generated COT rationales can mitigate these issues, highlighting its positive effects on exploration and decision-making. We also assess various exploration mechanisms to improve RLFT for LLMs. Section Summary. In this section, we explore the limitations of large language models, LLMs, in decision-making scenarios, identifying three main failure modes: greediness, frequency bias, and the knowing-doing gap. We propose reinforcement learning fine-tuning, RLFT, on self-generated chain-of-thought rationales to enhance LLM's exploration and decision-making abilities, while also evaluating various exploration strategies to address these shortcomings. Section: Methodology. In this section, we describe our methodology, focusing on reinforcement learning fine-tuning, RLFT. Our RLFT method involves fine-tuning using self-generated chain-of-thought, COT, rationales based on rewards from interacting with the environment. Through RLFT, we iteratively improve our reasoning process, prioritizing COT patterns and actions that yield higher rewards. For context representation, at each step, we input instructions, output instructions, and the latest interaction history. This history includes the most recent states, actions, and rewards. We choose task-specific instructions instead of a generic template, which helps the agent understand observations, possible actions, and its goals. Thus, the context is formed by combining the instruction and history tokens. When generating action tokens, we include both caught reasoning tokens and the action to be taken. We use an extraction function to derive the action from the reasoning tokens. If no valid action is found, a random action is executed. We prefer a flexible output format to allow for better reasoning refinement. We set a token generation limit for our outputs. To encourage valid actions, we add a reward shaping term alongside the environment reward. If we cannot extract a valid action, we apply a reward penalty. We normalize rewards to prevent bias in optimization. For fine-tuning, we use a clipping objective with an additional constraint to the reference policy. We implement a Monte Carlo baseline for environments with fixed episode lengths and learn a separate state value head for variable lengths, using generalized advantage estimation. More details on implementation and training can be found in the appendix. In our experiments, we analyze the impact of fine-tuning the Gemma 2 models in multi-armed bandit, MAB, and contextual bandit, CB, settings, as well as a text-based version of tic-tac-toe. We compare models of different scales and examine common failure modes in MAB scenarios, such as greediness and frequency bias. We also explore the effects of fine-tuning on self-generated and expert rationales, and the impact of exploration mechanisms on performance. For our environments, we utilize text-based MAB scenarios that highlight the exploration-exploitation trade-off. We focus on specific variants and report results for MABs with different arms and payoff distributions. We also consider varying levels of stochasticity and limit the interaction steps. Our comparisons include common baselines like upper confidence bound, UCB, and a random agent. Additionally, we use the text-based tic-tac-toe environment, which presents clear state transitions. Previous studies have shown that frontier models struggle in this setting, making it a suitable target for evaluating RLFT. Further details on our environment and training setup are provided in the appendix. Section Summary. In this section, we describe our reinforcement learning fine-tuning, RLFT, methodology, which enhances decision-making by refining reasoning through self-generated caught rationales based on rewards from environment interactions. We also outline our experimental setup using multi-armed bandits and tic-tac-toe to evaluate the performance of our approach across different model scales and conditions. Section. Why do LLMs perform suboptimally in decision-making? In this section, we explore why large language models, LLMs, do not perform well in decision-making and identify three common issues: greediness, frequency bias, and the knowing-doing gap. We analyze the Gemma 2 models using specific input contexts to highlight these failure modes. Our analysis focuses on a particular instance from our multi-armed bandit, MAB, experiments across three model sizes, revealing that these issues persist regardless of the model scale. First, we discuss greediness, where the LLM tends to overly favor the best performing action from a limited set of options it has encountered. We demonstrate this by showing the average action coverage of Gemma 2 models of different sizes over multiple MABs. We define action coverage as the proportion of available actions that have been selected at least once. For example, with 10 arms, the 2B model covers a small fraction of actions, while the larger models cover slightly more, leaving many actions unexplored. This tendency to favor high-reward actions leads to a premature commitment to a greedy strategy, resulting in stagnation and action coverage. As we increase the number of arms, this greediness becomes more pronounced, and the regret remains high compared to the upper confidence bound, UCB, method, even though the models perform better than a random agent. Next, we address frequency bias, where the model repeatedly chooses the most frequently selected action, even if it yields low rewards. We analyze how the frequency of actions affects the model's behavior by creating context histories with varying repetitions of the last action. We categorize actions as frequent, greedy, or other, and find that the 2B model struggles with repeated actions, showing decreased uncertainty as repetitions increase. In contrast, the 27B model manages to avoid frequency bias but still exhibits greediness. This suggests that frequency bias may stem from supervised pre-training, indicating a need for reinforcement learning as a potential solution. Lastly, we examine the knowing-doing gap, where the model understands the UCB algorithm but fails to act optimally based on that knowledge. We task the 27B model with producing UCB values and then acting on them. We find that while the model accurately computes UCB values 87% of the time, it often opts for the greedy action instead of the optimal one. This discrepancy underscores the limitations of LLMs in translating knowledge into effective action. Section Summary. In this section, we identify 3 key failure modes that lead to suboptimal performance of LLMs in decision-making. Greediness, where models favor high-reward actions too early. Frequency bias, where they repeatedly select frequently occurring but low-reward actions. And the knowing-doing gap, where models understand the optimal strategy but often choose suboptimal actions. Our analyses reveal that these issues persist across different model scales, highlighting the need for improved exploration strategies. Section: Effectiveness of RL Fine-Tuning. In this section, we examine the impact of reinforcement learning fine-tuning, RLFT, on cumulative regret in relation to the optimal policy and whether it addresses the identified failure modes. We fine-tune the GEMMA 2 models, both 2B and 9B, using self-generated chain of thought, COT, rationales over 30,000 updates with a total batch size of 128. To prevent memorization of reward distributions, we keep a pool of 512 multi-armed bandits, MABs, and randomly choose 16 for each rollout. We note that RLFT reduces regret, as shown in our results across different model sizes and scenarios. The LLMs outperform a random baseline, and RLFT significantly decreases regret for both the 2B and 9B models. For the 2B model, RLFT reduces the gap to larger models and upper confidence bound, UCB, strategies. We also see similar regret reduction for the 9B model, although the lower cumulative regret compared to UCB after 50 steps is influenced by limited interactions, yet the overall trends are evident. We repeat RLFT for contextual bandits, CBs, and observe similar improvements for the 2B model. This indicates that reinforcing self-generated COT rationales in relation to environmental rewards enhances performance in straightforward decision-making tasks. Additionally, RLFT helps reduce greediness, as we see an increase in action coverage after 30,000 updates, despite an initial decrease at 10,000 updates. This pattern is consistent across different scenarios, showing that RLFT encourages exploration and lessens greediness. Moreover, RLFT addresses frequency bias, as we notice a significant drop in the frequency of common actions and an increase in less frequent actions, although some high-frequency actions remain prevalent. While RLFT promotes exploration and reduces regret, we find that action coverage is still not optimal. We explore various classic and LLM-specific exploration strategies, including trying all actions initially, greedy approaches, context randomization, context summarization, self-correction, self-consistency, and exploration bonuses. Our findings reveal that the simple try-all strategy yields the most significant performance gains, with the 27B model nearly matching the optimal UCB agent. This suggests that LLMs need sufficient information about the optimality of actions to make better choices. We also find that a straightforward exploration bonus during RLFT greatly enhances exploration and reduces regret compared to standard RLFT, highlighting the importance of reward shaping in fine-tuning LLMs for decision-making tasks. Next, we assess RLFT in the context of tic-tac-toe, where we fine-tune against various opponents. Our results show that RLFT significantly boosts the win rate of the 2B model against all opponents compared to in-context learning, ICL. For instance, against a random agent, the average win rate increases from 15% to 75%. The model even manages to draw against the optimal MCTS baseline, demonstrating RLFT's effectiveness in decision-making. We also investigate the role of COT reasoning in RLFT performance. Our experiments show that without COT, RLFT struggles to match the performance of ICL with COT, emphasizing COT's critical role in exploration and rationalization. Furthermore, we create two expert datasets for behavior cloning, one with COT and one without, and find that both successfully mimic expert behavior, achieving comparable regret to UCB. This reinforces the value of expert data in decision-making. Lastly, we explore how varying the thinking time during RLFT affects performance. Reducing the time leads to poor outcomes, as the agent cannot rationalize its decisions, while increasing it improves performance significantly. This reflects the agent's ability to utilize additional tokens effectively, aligning with recent findings in mathematical reasoning.